Pues mucho gusto.
Igualmente, el gusto es mío.
Bueno, perfecto. Pues si quiere empezamos ya, son las 12:05. Buenos días, buenas tardes, ¿sí? Días para Ensenada, buenas tardes para Ceú. Esto es un placer nuevamente pues estar reunidos como cada miércoles, pero a diferencia pues han habido coloquios extraordinarios los martes o los jueves, de los cuales nos hemos podido también degustar. Hoy pues tenemos el honor, la fortuna de tener a Brisa Mancillas. Muchos de ustedes ya la conocen. Ella hizo su maestría aquí en CEU, bajo la supervisión de Vladimir Ávila, ¿sí? Su doctorado lo hizo en el Observatorio de París, bajo la supervisión de David Balsavó. Terminó hace un año, ¿sí? Y está junta a dicho observatorio. Pues adelante, Brisa, coméntanos acerca del tema de la plática que tienes para hoy. Bienvenida, adelante.
Muchas gracias. Si no les importa, voy a darle en inglés. Si están de acuerdo.
Sí, no te preocupes. Perfecto, adelante.
Okay, well, thank you very much for this introduction. So I am Brisa Mancillas, and I just finished my PhD in the Observatoire de Paris. So the title of my talk is Extending the Realm of Galaxies to the Low Surface Brightness Universe. So as a brief summary, I'm going to give you a general introduction, which includes the theoretical side, and a brief summary also on the observations. Well, I will start with observations and I will continue with the theoretical side, and I will talk about my several projects that I developed during my PhD, and also I am still working with. But well, let me start from the beginning. So we know that our first instrument to observe the sky is, can you see me? Okay, our main instrument to observe the sky is our eye. So we can observe basically with around 60 magnitudes per second square. And just with naked eye, we can observe some structures from the Milky Way, as you see here, some maybe the center of the universe and some substructures around. But if we are lucky, we can observe the central part of the Andromeda galaxy, which is, if we are lucky to have a very dark night, we can observe the central part. However, if we can be able to observe the whole structure, well, that we believe what is the whole structure of the Milky Way, we can observe on this size the Milky Way in a comparison with the moon. Okay, everything has changed with the invention of the telescope, let's say with this primitive telescope from, as I show you here, this replica from Newton's in the 1672. And now with the modern facilities with the Sloan, that is basically the survey that provides us the astronomical images to model the galaxy evolution and to study the galaxies. Okay, so but we should ask ourselves how, well, maybe we could ask ourselves how it looks like the Andromeda or other objects in the universe if we can be able to observe with the naked eye and reach the surface brightness of the Sloan, which is 26 magnitudes per second square. So we will observe Andromeda with this around 4 angular size of the full moon. But of course, there are many things to see. There are many, we can go deeper, of course. And as I show you here in this image, which is a luminance filter of the image of the nearby galaxies. And this is a superposition of images from the Sloan and the photographic plates, and we can observe our whole structures around these galaxies. And here's some tidal tails emanating from this kind of galaxies, or some like umbrella shapes, or a whole stellar halos around this type of galaxy. So, but of course, we can say why, why Sloan or other instruments don't have this depth, why we don't reach this depth in surface brightness magnitude. Well, this is because there are instrumental and technical challenges between others that I will talk about. So the first one is the sky brightness. So usually we reach 22 magnitudes per second square. And well, a possible solution is integrated long enough, as we know. But even if we go outside of the planet, we can reach 1.5 magnitude more, but still we can have the zodiac light and so on. So other technical challenge that we have is internal reflections. So when the light coming from some source or even the reflection light, we can touch the instrument and create artificial structures on the CCDs. So even if we reach this 26 magnitudes per second squared, we can have this problem. And a potential solution is that we can make a simple optical arrangement and make a clever and better observing strategies. And a third problem that we can have is the scatter light. Even if we reach 29 magnitudes per second squared, we have the light from the source and the light from the point spread function that contaminate the CCDs. And this is something that a problem that we can have. So the possible solution is make a meticulous characterization of the PSF. So this is the technical problems and the technical and instrumental problems, but also we have another more important problem, which is the sky pollution. And we call it galactic cirrus, which basically it is the far infrared millimetric emission from a coal dust located in the Milky Way. So this emission, people say that is coming from the center of the Milky Way, of our own galaxy, but actually it's not, because there are very few spots where we can observe the objects, as I show you here in this frame from the MATLAB survey, which has a depth of 29 magnitudes per second squared. So here we see in this frame that half of the frame is full of these galactic cirrus. So we really need to be an expertise astronomer, professional astronomer, to distinguish these substructures coming from the galaxies coming from the galactic cirrus. So, well, currently there are, this is the state of the art ground-based optical telescope. The first one is the Canada-France-Hawaii telescope. I was part of the survey coming from this telescope, which reaches a magnitude of 29 magnitudes per second square. And it has a complex CCD of 40 CCDs that make a camera. There is also the Subaru telescope, which has 8 meters in total. And the most advanced telescope now is the Dragonfly Telephoto Array, which has 48 lenses divided into 2 sections, as you see here. And they can reach between 30 and 32 magnitudes per second square. They are really, really deep. Of course, it's in the space-based telescope exists Hubble and the others which are coming. So here I wanted to show you also this. This is the deepest image of nearby galaxy, which is C00-118. Here we are observing fine galaxies. This is a superposition between the Sloan, all the color part is Sloan, plus the GTC, the Gran Telescopio from Canarias, with 8 hours of integration. And we can observe all this area, shaded area is coming from the galactic cirrus, but we can observe some extended structures here that in another picture we will see them better. So, but there are fundamental questions. It is possible to go 10 times deeper. Yes, we are trying to go people are trying to go deeper. And why do we need to reach surface brightness magnitudes of around 30 or 32 magnitudes per second square? Well, because there are several cosmological problems which are related with the depth of these images with which we calibrate the models and we describe the galaxy evolution. So I will mention some of them. So the first of all, we can have resolved stellar halos, and we can, with the resolved stellar halos, we can make a realistic quantitative characterization of cosmological predictions. And here, for example, I show you this image, this simulated image of a halo, comparing two surface brightness limits, which one is 29 magnitudes per second square. And we, for example, here we are missing all the traces and satellites around this galaxy. And when we go deeper with 33 magnitudes per second square, we can observe all these kind of substructures around. And also we observe the growing or a factor of 3 larger galaxy than we used to see with this kind of images. So I will talk later about this simulation, which is a work I was working with. And also, as a matter of observational side, we have here Andromeda. Andromeda was observed with the PANDAS survey with the raw stellar counts. And also, for example, before we believed that Andromeda has this angular size, and the reality it has all this size, which is connected also with M33, the companion of this galaxy. And we can see how huge it is, this galaxy. So we are having, maybe we also can tackle this problem, this classical problem of the cosmological paradigm, which is the missing satellite. So also, I wanted to show you this image of NGC 474. Maybe you have seen this image very often now, that we can see some substructures, but they are very fine substructures with this value of 26 magnitudes per second square with Sloan. But when we observe with other kind of surveys, such as Mancillas, with 29 magnitudes per second square, we can appreciate and we can really see all these substructures, these semicircle substructures with more resolution, and all these tails and streams that we cannot be able to observe very well with Sloan. So also, if we want to, what else we can do if we want to go deeper with deeper observations and so on? Well, we can trace the large scale structures in the intergalactic medium and see, for example, I am showing you here the Virgo cluster and how we are coming from 21 to 29 magnitudes per second square. And we can see all this cluster, which is the nearest one to us, in all its glory, and observe how we can illuminate all this intracluster light, and we can characterize all these substructures that we are observing. So this is in the part of the observational side. In the theoretical context, I want to tell you what is the importance of low surface brightness science or low surface brightness galaxies and substructures. But let me first give you like a broad or very brief summary of the theoretical part. So to describe the galaxy evolution, of course, we need a cosmological framework, which includes the lambda cold dark matter. So in this framework, all the cosmic structures are coming from density perturbations generated from quantum fluctuations in the expansion of the universe. And these perturbations evolve gravitationally, but separate from the expansion of the universe. And after collapse or collapse for self-gravitating and become some structure that we call lambda cold dark matter halos. So this picture includes several facts, which are the cosmological theories that include the Big Bang and inflation, the physical models, which are beyond the standard model of particles, the astrophysical models that include the hierarchical clustering, or the physics that include the cosmic microwave background radiation. So for the galaxy formation and evolution, we need lambda cold dark matter halos, a gas cooling process, a disk formation without secular evolution, mergers, of course, star formation, and feedback from AGN and supernova. So, well, according to this lambda cold dark matter halos, so the formation of large scale structures are dominated by the gravitational dynamics of dark matter. And this process occurs in the hierarchical way and culminates with the assembly of dark matter halos. Since these dark matter halos are structures in virial equilibrium, they attract and incorporate a fraction of baryons into their central regions that are leading to the formation of galaxies. But of course, these halos are defined by a set of several properties, such as everybody knows that these properties are the mass, the concentration, and the angular momentum. That, in your instance, is going to determine the amount of gas and its distribution of angular momentum. So in the part of the astrophysical point of view, these properties are going to be set for the processes of star formation and their feedback with the interstellar medium, the secular evolution, as I mentioned, the mergers, and formation or the AGN from supermassive black holes, and feedback from interstellar medium and AGN phases. So this is like a broad and how we start. And I also would like to mention that there is main changes of the universe over the cosmic time. So there are 3 phases. The first one is the peak of the cosmic star formation, which happens around redshift around 2, which rapidly decreases at around 0, because the gas, all the stars, the formation of the stars consume the gas, or because the gas is heated and finished. So another thing is that the central supermassive black holes grows as well. So as the star formation is happening, the black holes are also growing up. Why? Because the same component that feed the star formation and the black hole formations is the gas. So when a galaxy is accreting gas, some part of the gas go to form stars, and another part is to go to form black holes. And another thing is the changes in the galaxy morphology. So morphological mix changes over the time. Why? So according to the Hubble diagram that I show you here, so there are 2 main groups of galaxies. First we have the spiral galaxies, which are rotational supported, and we have elliptical galaxies, which are dispersion dominated. So with the time, the universe passed to go from more dominated rotational supported systems to less dominated rotational supported systems, and becomes a more dispersion dominated. But why? This is because the mergers, and because the universe has this gravitation component, well, gravitation force that is acting mainly, and all the structures are having are collapsing or are merging. For example, if you have a merge between 2 spiral galaxies, what gravity makes is to disequilibrate these rotational orbits and make more dispersional system. So this is like a general picture in terms of how galaxy evolution happened. But of course, the galaxy evolution is well described for this broad aspect, but it has important concernings, or as people used to say, the devil is in the details. So we really don't have a real understanding between the star formation and supernova processes. When some supernova happens, so there is stellar winds, and we don't know exactly how this kind of process affect the galaxy formation. How is the effects on how we are modeling the galaxy evolution, but also in the case of AGN feedback, we don't know, for example, how this process affects also the rest of the formation of the structures. So when you have a jet of energy, an AGN, so all the gas can be heated and then stop the star formation, or the gas can be expelled away and after come back and may delay the star formation. So we really don't know how it's happened, these processes. So another thing is, for example, we don't know at all how is the RAM pressure stripping or the tidal heating, which are environmental processes. So it's believed that people understand at all because they have been able to model it, but I think we should be able to be more careful because we don't have enough data to model this kind of processes. And low surface brightness galaxies and structures should be like a solution to explain this kind of all these processes that I am mentioning. So in terms of how is the modeling galaxy formation, so well, for many years is the semi-analytical models, cosmological simulations have explained it very well. How is this process? They represent the dark matter skeleton to build up galaxies and so on. But they lack of realism because all we use analytical recipes, which don't need only to know how many baryons we have the gas fraction, gas baryonic fraction, stellar fraction. We also need to know the resolution baryons and see how they are distributed. So for this, what is something that they can model the galaxy formation are the full hydrodynamical simulations. And some of the state-of-the-art that currently exist, they are Illustris TNG, Horizon AGN, Eagle, Bella, and others. So they have so much more better resolution. For example, they have around 100 parsec spatial resolution, 10 to the 4 and mass resolution. Of course, we also need numerical recipes, but here is more realistic galaxies because we can be able to have resolution in baryons. So this is the general picture I wanted to give. So, but why low surface brightness galaxies will be important in the future? Okay, well, yes, all our empirical knowledge on galaxy evolution and the theoretical calibration for models is based in a minority of the galaxy population in the universe and in surface brightness systems. So why surveys like the slow one becomes incomplete at 23 magnitudes per second square, and the galaxy evolution models are based in high surface brightness systems that are higher than 23 magnitudes per second square. So we know that several studies know that the bulk of low surface brightness galaxy populations lies below this surface brightness threshold, and several processes not clearly understood. Those processes that I mentioned before can be so much more sensitive, explored, and described with low surface brightness galaxies and substructures. I mentioned here again the supernova, the AGN feedback, the environmental processes, galaxy mass assembly, the large scale structure. So this is the general motivation I want to show you. And well, here, as Michael Disney say in the 70s, so the galaxies are like iceberg, and what is seen above the sky background maybe is not reliable measurement of what lies underneath. Of course, as I was mentioned, so all the low surface brightness galaxies plus the dark matter sector, we need to really understand it. So we declare, or we consider low surface brightness galaxies, those which are deeper than 23 magnitudes per second square. Usually they are dwarf galaxies, ultra-faint dwarf spherical galaxies, gas-rich regular with low star formation, the famous ultra-diffuse galaxies that I will talk about them later. And there are also massive G, and these galaxies are like a very famous Malin 1 that you can search it, and it's a very interesting galaxy. So, well, now the rest of my talk, I'm gonna speak about the projects I developed during my PhD within the science of low surface brightness. And the first one, it was to study the mass assembly of galaxies, of early type galaxies, below defined structures as a result of galaxy mergers. So galaxy mergers, we know that in the hierarchical framework of galaxy formations, mergers play a major role in the assembly of galaxies. So as I show you here, this merger tree that illustrates the formation history of dark matter halo that is traced by its progenitors. So basically, we have the type of galaxy mergers are divided in three main classes. The first one is according to the number of members. The first one is a binary and includes like these galaxies like the antenna galaxy, this beautiful galaxy, or multiple that includes, for example, the Stefan quintet. And they are according to the mass ratio. They can be major or minor mergers, and according to the gas content, if they are wet, dry, damp, or mixed, which means how is the gas, if they are rich gas or poor gas. So what is the question that this part of my work try to answer is, as I was mentioned before, is how to derive the merger history of early type galaxies from the surrounding fine structures, tidal tails, streams, and shells. So here I show you this atlas image from the Hubble Space Telescopes, and where we can see a zoo of all kinds of interactions and mergers. And here the idea was to analyze an aerodynamical numerical simulations within a cosmological context and make a comprehensive interpretation of these low surface brightness structures and its properties, and try to determine or to reconstruct the mass assembly history of an early type galaxy. So there is an active discussion on the role that major versus minor mergers between gas-rich, gas-poor mergers versus cold gas accretion, the morphological class, environment, and the redshift. So fine structures observed with deep imaging programs can allow us with the diffuse light and in the outer stellar populations around a large number of galaxies. How is this distribution, and answer some questions. So just briefly, the major mergers can happen between two spirals, which are gas-rich and produce long stellar tidal tails, or it can happen also between two early type galaxies, which usually are gas poor and usually don't produce any kind of tidal tails, or minor mergers that involves gas poor and they involve dwarf satellites and produce narrow tidal tails, which are wrapping around the central galaxy, tracing the orbits of the satellites that was surrounding them. So, well, this is, I will briefly mention also that I was part of this survey, which is the MATLAS, is a large program survey, which means mass assembly of early type galaxies with their fine stellar structures. And they basically make an investigation of the mass assembly of early type galaxies with extremely deep optical images from the camera from CFHT. They reach 29 magnitudes per second square in the G band. And also results they have providing us LSB optimized the surveys, which are detecting new prominent structures that change the apparent morphology of galaxies. And also they have providing us examples of each type of observed structures that they have been make a phenomenological classification of each kind of these substructures that I will talk about. So here we have the tidal tails indicated here, the stellar streams and shells. And for example, tidal tails are defined as elongated structures and that emanate from the primary galaxy. Here we have two primary galaxies. And we see here the tidal emanating from this galaxy and are made during the major mergers, and the material is expelled from the galaxies, as I was mentioned. In the case of stellar strips, we have narrow filaments and long filaments. They are finer than 26 magnitudes per second square, and they trace the past minor mergers. And here the material is emanating from the low mass companion. And after we have these spectacular substructures called shell substructures around NGC 474, which are circular shapes and shape-edged structures. And usually they are numerous, as you can see here, around the central galaxy. And they trace intermediate mass mergers. So, well, I use a numerical simulation following this approach, where a merger and accretion histories were extracted from a lambda called matter halo in a cosmological numerical simulation from Martic in the 2009. And after we make a high resolution resimulation where the accretion histories are resimulated at a much higher resolution, and each halo is replaced by a realistic galaxy containing gas, stars, and dark matter in order to make it more realistic. So here I show you a wide frame of our halo, how it was from zeta 2 to zeta 0. So here I show you that the halo undergoes two main phases. The first one was an intense phase of minor and intermediate mass mergers. A second phase that I am showing you here is a quiescent period. Not an important mergers happen, just very teeny minor mergers that usually are undetectable. And a third phase where a major merger event takes place. So here I show you the evolution of the MOOC surface brightness maps. We did it for 3 different projections, and we used 2 cuts in surface brightness. One is in 29 magnitudes per second square, which correspond to the MATLAS survey. and the other one is 33, the deepest one, 33 meters per second squared, which corresponds to the Mancillas collaboration with David Baskerville. So here I wanted to show you also how is the evolution of the stellar mass from both components, the in situ mass, which is a mass is the mass produced inside the galaxy itself, and the accreted mass, which is this mass that is coming from all the mergers that took place during the evolution of the galaxy. And here I show you a mosaic of these surface brightness images, and we can see how initially was the halo in the galaxy, and as it was evolving in this direction, so we start to see how all the progenitors or the satellites were down the potential they will form frame now. So the frame reaction, and we classify it again as a tidal tails, stellar streams and shells. We were a team of 5 as professional astronomers who made the identification for the 3 different projections. Here I indicated with the white arrow, the substructure here. This is the same object, but in 2 different projections. And the case here for the stellar streams. So after what I made, it was a comparison between 3 selected galaxies from the MATLAB surveys. They are real galaxies, and some objects of the stage from the simulation. And we can see how similar are these substructures with our numerical simulations. So the next step, the next step was to make the evolution of the number of tidal tails. And here I show you the number of the frequency of these substructures as a function of the time for the 2 cuts in surface brightness magnitudes. The green line corresponds to the 29 meters per second squared, and the black with the yellow shaded area correspond to the deepest magnitude, 33 meters per second squared. And for the 3 different projections, XY, XZ, and YZ. So for the case of tidal tails, the first thing we noticed it was that we didn't find a dependence on the surface brightness sensibility. So we can see that the fashion of the curves follow the same trend, and they don't have an important difference. So we can observe them mainly in both surface brightness. There is not a strong dependence in the projection. We can observe them in all directions. And I show you here, for example, the 3 different projections of the same object, and we can observe them. So after we have streams, this is the same plot for the case of the streams. And here, the first thing to notice is that we found a strong dependence on the surface brightness. Here, the curves, we found an important gap between the 2 curves. Having this object as well as this galaxy doesn't present too much or doesn't present this fine feature that we can observe here. So we didn't find a dependence on the projection. They are identified in all directions. So they are visible in all during the whole evolution of the simulation, and we can see that they reach a peak in 10 gigayears, so which are within the phase of the quiescent phase. And third, we have shell galaxies. In the case of shell galaxies, the first thing to notice is, yes, we have a strong dependence on the projection. We observe so much more features here in this plane, zeta plane, than in the XY or Y zeta plane. So we also we found a slight dependence on the surface brightness limit. We found here a little gap between the 2 surface brightness cuts, and we can check, or we can see it in this object. So, well, as a matter of summary, what we found is the shell galaxies are those substructures which last more or has a largest survival time. And the streams are those which are more dependent on the surface brightness sensitivity. And the orientation dependence is more important in the case of shells, is very important. So just concluding remarks of this part of the work. Well, tidal tails are resulting from major events, shells from major and intermediate mass mergers. So tidal tails and shells have long survival times between 2 and 3 gigayears, but the streams remains visible in all phases of the galaxy evolution. So the detection of stellar streams are strongly dependent on the surface brightness limit. We can observe between 2 and 3 times more streams with a surface brightness of 32 magnitudes per second squared than with 29. And the it's a strong projection of the system. So now I'd like to show you. I will show you other part of the work. So this is the molecular gas content in low brightness galaxies and ultra-diffuse galaxies. So the question was there are, and what is the formation mechanism if there is a phase wrapping or a space wrapping scenario? Also, if there is molecular gas in ultra-diffuse galaxies, because people have assumed that there is not gas content, so we will try to check if it is true or not. So, well, fission shells of those galaxies harbor shells structures are elliptical, so extragalaxies, which exhibit brightness shapes and shape were detected in ARP, in ARP in the 16th, and we can see these barely shells. But the largest catalog that we have so far is from Malin and Carter in the 18th, and we can see this prototype NGC 3923. And we can observe this substructure here. So I will mention some shell galaxy properties. Well, they are detected in elliptical, lenticular, and this is zero galaxies, and are presented in environments of low galaxy density. They are usually three-dimensional structures. They can have prolate or oblate geometries. They appear as a concentric semicirculars around galaxies with high ellipticity and tend to be aligned with the major axis. It depends if they are oblate or prolate. And the shell structures are can be randomly spread around the galaxy center of E0 elliptical galaxies, such as this famous one, NGC 474. And usually they are numerous and appear over a large range of radius. So the distance between the two successive shells increases with the distance of the center of the galaxy. Okay, so here I just wanted to show you again this prototype, NGC 3934, observed with the CFHT. And here they detected up to 42 shell substructures. And here they are indicated here with the red arrows, and we can see a detailed zooming of this galaxy, how these shell substructures are formed around the central galaxy. So they believe that shell systems are originated from 2 or more progenitors, as Bilek mentioned. So as I was mentioned, we also try to prove what is the formation mechanism of this kind of shell structures. And the formation mechanism that favor this scenario is the phase wrapping. So in the phase wrapping scenario, the stars from a companion are liberated by tidal tails. They start to oscillate in the potential well, as I show you here in this diagram of the period as a function of the radius. So these stars start to oscillate in the potential of a primary galaxy and sharp these aged forms as an outward propagating wave at their apocenters. So as I am showing you here, so this wave touch the apocenters, which has the maximum distance and the maximum energy, and start to oscillate, reduce the distance with respect to the center of the galaxy. And the density, the star density that they accumulate in these apocenters decreases as they are going, decreasing the radius. So there could be radial oscillations in a prolate potential, as I show you in this image, which result in an alternate formation of shells. They could, we also can have less radial oscillations with angular momentum and form shells around this equatorial plane in the case of late galaxies. So, well, to study this, we wanted to study how the molecular gas content and how is the distribution. So we made a sample of selected shell galaxies. We studied 9 galaxies. They were observed from the northern hemisphere, previously also observed in H1 21 centimeters, and in CO in the millimeter domain. So here I show you 7 of them, these galaxies. And here the circles indicates the beams of the telescope, the IRAM 30 meters telescope. So the 11 arc-second indicates a transition line between 2 to 1, 1 to 0, and the 23, no, 2 to 1, and the 23 indicates a transition line of 2 to 1 mission line. So here we have again NGC 474. As you can see here, we were observing in the center because this galaxy was observed before, and they didn't form molecular gas in the center. But all galaxies, we make several points like this NGC 3934. So here, just quickly, I show you several properties. They have an H1 mass between 10 to the 8 to 10 to the 10. Atomic gas or molecular gas between 10 to the 8 to 10 to the 10 again. So as a result, I will mention that each shell galaxy was first observed in the center because we wanted to observe first the center before to be observed in shell regions. Why? Because shells are expected to come from infalling gas-rich satellites, and we expect that the gas is distributed and falling down in the center and not spread around these substructures. So what we found, it was that 6 of our sample of 9 galaxies has but only 3 have a molecular gas in shell substructures, which was the case of R10, NGC 5655, and NGC 5934. So here I show you the spectrum of 10. So these circles again, the point, we have structures around and all the detection that we did. And here I show you the stacking of these substructures. So here I show you the other galaxy, NGC 3655. So here we found an emission of southern shell of this galaxy. Here I show you the mapping, and here is the spectra that show 2 horn shape in the case of these southern shell substructures. And we have the spectra for the case of NGC 3934, which we found the molecular gas content in the outer shell substructures that here we need a deepest image with a higher surface brightness magnitude, but here there is a shell substructures and here as well. And here the spectra are showing a 2-horn shape, which indicates that maybe there is a contribution of angular momentum, or there is a contribution from the central part of the galaxy. So, okay, but what is the relation between the atomic and the molecular gas in shell galaxies? Well, as I was mentioned previously, gas is dissipative, and it's surprising to find gas in shells. So the diffuse gas is expected to fall into the center. The dense gas close to experience so much more less dissipation than diffuse gas. And the spatial distribution of stellar gases are already reproduced in shell formation models that we have here a fiducial example. This is Centaurus A. Centaurus are shown with a molecular gas content of 10 to the 7 solar masses. Here, the white isocontours represents the H1 gas, while the red isocontours correspond to the iron beams and correspond to the areas where they observe CO. So these molecular clouds have a similar behavior to the stellar components. So in our previous galaxies, we can say that our detection support these models. Okay, so well, the CO velocity in shells, the CO profiles in shells are broad and show two-horn shape in both of our galaxies. This is because the CO beam covers a large shell area, and the material is not only radial, but keeps a tangential velocity of the apocenter. So, and the material also can be positive and negative angular momentum with respect to the galaxy, with respect to the projection of the galaxy. So there is also a comparison with H1 in shells. So H1 mapped was found in 6 shell galaxies, and H1 in NGC 3655 were associated with other stellar shell. It was compatible kinematics. And H1 and CO emission in the shells explained by clumpy gas with a low filling factor and with low dissipation. So as a concluding remarks, I can say that molecular gas was again detected in the center of 6 shell galaxies. The molecular gas lies between 10 to the 9 in shells of R10 and 10 to the 8 solar masses in southern shell of NGC 3655 and 10 to the 8 also in the 2 detected shells of NGC 3554. So the conclusion was that the phase wrapping scenario in an early radial orbit played a major role for the case of R10 and NGC 3655. And the gas detected in shells supported the clumpiness and low dissipation of large part of interstellar medium. And these two-horn shape in line profiles that I show in 2 of the galaxies indicate both positive and negative angular momentum and relative to the primary galaxy. So we are doing now, well, we performed observations with NOEMA interferometer in order to mapping the CO and try to disentangle this phenomena that we observe in these two galaxies. We are currently reducing the data and saying what is the source of this two-horn shape in the spectrum. So, well, now I'm going to talk about the ultra-diffuse galaxies. So, well, as many of you maybe should know, detection of ultra-diffuse galaxies is currently most of the lively debates of the past 5 years, because it was recently discovered by Mando Kuhn in 2015. And he was claiming that it was a galaxy dominated by dark matter. So we were motivated for this finding, and we tried to check also what is the molecular gas or H1 gas in this kind of galaxy. So, but for definition, some of the properties are that they are fine galaxies that has a surface brightness magnitude between 24 and 28 magnitudes per second square. They have a large effective radius, which are larger than 1.4 kiloparsecs, and they are considered as a dwarf in terms of luminosity because they have very low luminosity, or jet giants in terms of size because they are Milky Way sized, for example. They are spun in a wide range of environments, either clusters or filaments, and it's supposed they are extremely dark matter dominated. For example, they have stellar masses between 10 to the 7 and 10 to the 8 solar masses, while the dynamical mass is 10 to the 10 solar masses. So the origin and formation mechanisms of these UDGs, as I say, is extremely in a high discussion, but there are several formation scenarios. So they say that they are head-on collision of galaxies or tidal stripping of galaxies within clusters. Or UDGs can also be rapidly rotating tail of the distribution of dwarf galaxies. Size and surface brightness of galaxies are related to its spin, according to Amorisco and Loew. And the gas mass content, well, the gas role is very unclear because, as I say, people assume they don't have gas. So the hypothesis is that the gas fall into dark halos, settles into a rotational supporting disk at the lowest energy state, given its specific angular momentum. So the large sizes of UDGs can arise from very high angular momentum gas, and the stars are formed following this distribution. So here in this project, we made a CO120 221 line survey of 12 selected ultra-diffuse galaxies with IRAM 30 meters telescope. This was a project between Monica Rodriguez, she's also she's a Mexican doing science in Europe also, with David Valls-Gabaud, with François Combs and me. And this is the first large survey of molecular gas content in ultra-diffuse galaxy. And we include targets such as a very red galaxies, the famous one, Dragonfly 44, that you can see here, and DigiSat 1, that is this point that we can confuse with this one, but this is the real galaxy is this. And we also include the blue or H1 rich and nearby target UDGs. So currently now there are a lot of galaxies. There are more than 4,000 galaxies detected, ultra-diffuse galaxy detected, but only if you had measurement redshifts at high precision, which is really the challenge to start to observe these galaxies or to characterize them, because we really need to know the distance of these galaxies. So as a preliminary results, here I show you, for example, the case of Dragonfly and the DigiSat 1. And so we observed that we found just upper limits. Well, in the case of H1, they have H1, but in the case of H2, we found only the upper limits that at 3 sigma, it was 10 to the 7 and 10 to the 8. So here, as you notice, we just have a noise. And well, the concluding remarks was that the observations resulted in no detection in spite of very long integration times. So the campaign at the IRAM 30 meters telescope, we observed the 12 ultra-diffuse galaxies with large masses. And well, we can say that we set just very stringent upper limits, 3 sigma on the upper molecular mass values, according to the standard CO to H2 conversion factor. And what we can say here is that the lack of cold gas, both in atomic and molecular phases, set stringent constraints on the current star formation efficiency in UDGs. And should this efficiency be the same as earlier times, it would imply a major revision of the star formation histories, and indeed the way the star formation proceeds in environments where the stellar and gas mass surface density are very low. So, well, which are the perspectives of this work that I have been working? So, well, the tidal tails, streams, and all these fine features can be detected in dozens of galaxies with new ground and space-based telescopes such as LSB, which is going to be working the next year, or I hope the next year, or Mancillas Space Telescope led by David Valls-Gabaud, and will allow you to understand the hierarchical formation in function of many parameters as the environment and masses. So now much more statistics can be gathered of many zoom-in simulations available in the literature, and also with machine learning technique, could be used of this viewing individual cases by eye. So there are some works like those from Wansley that have developed a neural networking algorithm to both identify and classify tidal debris around galaxies in deep images, but the technique is limited by the lack of comprehensive training samples. So we still need to use a visual identification. So there are also ideal algorithms that will connect the morphology of the detected features back to the physical parameters of the accretion event, such as the angular momentum, the mass accretion time. And so programs are already done in this front by Hendel and who use it, for example, morphological algorithms against controlled Tenebari simulations of accretion events. So also it's possible, well, this is, I didn't have so much, I already spent so much time, but I didn't have time to talk about some empirical approach that I working with Vladimir during my master thesis. So we can use this empirical approach to make spatial abundances of particular population of galaxies, such as these, those of galaxies and ultra-diffuse galaxies. And the CO well was detected in shells, but we need more spatial resolution to check the mechanism to see whether the gas in shells is indeed just outside the stellar shell. And this is what I am working with NOEM observations. And well, gas in UDGs should be searched more with H1 than with alpha star formation than CO. So I will stop here, and all your questions are welcome. Thank you.
Okay, thank you, Brisa. Thanks for a nice presentation. If you have questions in Spanish, English, Spanglish, or comments, are welcome. If you have questions, please raise your hand. Vladimir. Okay, Vladimir, go ahead. In Spanish or English, I don't know. What you want, okay.
Okay, I think in Spanish. I don't see anybody is spoken in English. Okay, Brisa, muy interesante, muy bonita tu reseña y el trabajo que has desarrollado durante tu tesis. Tengo una pregunta muy concreta con relación a esto de los caparazones, de los shells. Bueno, para 3 galaxias han encontrado que en estos shells hay gas, tienen gas CO, o sea, gas molecular. Y mi pregunta es, ¿qué densidades superficiales tiene ese gas detectado? Y si hay alguna evidencia de formación estelar asociada, digamos, a esas regiones con gas. Porque si no la hay, ¿por qué no? Porque si hay gas molecular, ¿por qué no hay formación estelar?
Sí, bueno, las densidades no las calculamos, pero sería un parámetro interesante para hacerlo. Pero sí, es justamente lo que tratamos de demostrar con las observaciones de CO, porque básicamente sí hay formación estelar, o sea, al menos en 3 de esas galaxias sí encontramos formación estelar en estos shells. Y ¿por qué? Porque lo que concluimos es que ese gas molecular se comporta como las estrellas, al menos en cuestión de movimientos, ¿no? Pero tiene mucho que ver también con el tipo de interacción que tuvo, si el gas fue, perdón, si el satélite era gas rich, perdón, si era rico en gas o no, y depende, o sea, de cómo se estaba dando la formación, de esta manera, como una onda que se está propagando, pues podría desatar la formación estelar. Entonces, en general, o sea, no esperábamos, en realidad es el primer trabajo que se hace sobre cómo se puede formar, sobre cómo se puede dar la formación estelar, y no esperábamos encontrar gas. Entonces, pues lo encontramos en su forma molecular y sí vimos que sí se da una formación estelar. Encontramos unos valores de 10 a la 8 masas solares. Entonces, sí existe, pero tiene que ver con el tipo de satélite con el que está interactuando y también el tipo de órbita, o sea, si va a llegar como una órbita radial o si va a llegar, depende de como que el parámetro de impacto, de cómo va a interactuar el satélite con la galaxia principal.
Claro, ok. Gracias, muy interesante.
Ok, muchas gracias, Vladimir. Adelante, Octavio. Adelante.
¿Qué tal, Brisa? Muy interesante y con mucho potencial todo lo que nos platicaste. Tengo 2 preguntas. Una es, ¿cuál es el estado de esta misión Messier? ¿Pronto se va a hacer o porque es muy interesante? Y la otra pregunta que tengo es, ¿qué necesitarían o qué tan lejos están? Es intuitivo conectar todas esas estructuras con la historia de acreción y de ensamblaje, pero de llegar a algo cuantitativo, ¿de qué depende? Del tamaño de la muestra, de tener muchos casos, de calibrarlo con simulaciones. ¿Qué tan lejos están de llegar a algo cuantitativo? Esas serían mis 2 preguntas.
Sí, perfecto. Bueno, de eso ya no hablé más porque como vieron es muchas cosas que hacer en esta ciencia del vaporío superficial. Pero mira, el estado de Messier no lo sé bien, o sea, yo sé que David está en todo el mundo buscando financiamiento, esta es la primera cosa que él está haciendo. está dando conferencias en todos lados y el proyecto ha pasado por varias fases. O sea, hay unas fases donde creo que sí le han aprobado cierta cantidad de dinero, otras donde, pues porque ya tiene competencias, especialmente creo que con los chinos. Entonces ya tiene competencias con ellos y lo que ha tratado de hacer son como colaboraciones, no sé más detalles, pero sé que sigue ahí como que en la lucha porque pues sí hay mucha ciencia que explotar, sobre todo porque va a ser un satélite que va a estar orbitando y va a ser mucho más fácil, ¿no? Estar observando estas subestructuras. Y bueno, el objetivo es estudiar el universo a gran escala, ¿no? Ahora, con respecto a lo que dices sobre la parte cuantitativa, sí, por supuesto que ahora mismo la gente está poniendo todas sus esperanzas, o estamos, porque yo también me incluyo, en el LSST, este telescopio que está en Chile y que pues se supone que ya va a empezar a observar, o no sé si ya han hecho también pruebas preliminares, y de ahí sí
El
vamos a
23.
tener una, sí, bueno, ahora con la pandemia pues no sabemos cómo se puede retrasar esto, pero la idea es que se está mapeando un campo muy amplio del cielo y se va a tener muchísima información, se van a tener muchísimas subestructuras y galaxias estudiadas a una profundidad muy alta. Entonces va a haber una completud en el survey que estamos esperando del LSST. Y bueno, además, pues de hecho, como la perspectiva de mi trabajo que hice es empezar como a caracterizar y empezar a hacerlos, a usar parámetros que no son morfológicos para caracterizar este tipo de subestructuras, pero hacerlas de manera estadística. Entonces, para esto, lo que estamos tratando de investigar ahora es usar Machine Learning, primero, para hacer una identificación automática de las subestructuras, porque estaremos de acuerdo que no voy a usar una inspección visual para caracterizar todas esas subestructuras, ¿no? Entonces tenemos que hacerlo primero de manera automática, pero pues todavía la inspección visual es necesaria porque pues se tienen que identificar bien estas subestructuras. Pero sí, las perspectivas a futuro son todos los datos que estamos esperando desde el LSST. También está Euclid, Euclid y WFIRST. Entonces, estos también tienen otros objetivos más relacionados a la cosmología, pero también van a traer un montón de datos que nosotros necesitamos analizar de manera estadística.
Muchas gracias.
Ok, gracias, Octavio. Pues no veo más manos levantadas. Yo le agradezco a Brisa por esa presentación. Si alguien quiere prender sus cámaras o hablar con ella, pues bienvenida. Muchas gracias, pues eres bienvenida y por aquí te esperamos cuando pase toda la pandemia.
Muchas gracias.
Bueno.
Muchas gracias a todos.